Hello all, welcome to the Basics.Academy. This is Solana Blockchain Fundamentals and Architecture, a 5 units, 3 credit course in the BSc Blockchain Technology program. Let's get into it. Today we are going to start with the second lecture of Introduction to Solana Blockchain, in which we will cover architecture. We will talk about what proof of history is and how proof of history and Tower BFT together forms the Solana's consensus algorithm. We are also going to look into accounts and programs. What does it mean by a clock before consensus? And how exactly Tower BFT voting works? What exactly are we going to cover today? First, we are going to go about Solana's building blocks, which includes accounts, programs, transactions, PDAs, which is programmable derived addresses, and CPI, cross program invocation. Then, what exactly is proof of history? And what do we mean by the clock before consensus idea that underlies everything else? After proof of history, we are going to see Tower BFT, which is Solana's PBFT style consensus that is built to exploit that shared clock. And at the end, we are going to have a quick intro about the remaining innovations which Solana blockchain offers. That includes Turbine, Gulfstream, Sealevel, pipelining, Cloudbreak, and archivers at a glance. Solana development splits into two halves. First is the on-chain program development. When we look into on-chain program development, it involves writing and deploying custom programs. Programs are smart contract equivalent on the Solana blockchain. Once the programs are deployed, anyone who knows how to communicate with a program can use it or send transactions to it. On Solana, the programs or smart contracts are primarily written in Rust language. Apart from that, it also supports C and C++. Looking at the second half, that involves client-side development, which is developing applications or dApps, decentralized applications that construct and send transactions which in turn interact with the on-chain programs or on-chain smart contracts. When we look into client-side development, there are some official SDKs which are being provided by the Solana developer ecosystem. If you are using Rust, go with Solana underscore SDK. If you are familiar with TypeScript, then go with @solana/kit, and it also includes the legacy one, which is @solana/web3.js. There are also community SDKs for Python, Java, C++, Go, and so on. First is the actual program or smart contract development, and second is the client-side development. So these are the two halves when it comes to Solana development. These are the core building blocks when it comes to Solana development. First and foremost is the accounts. No matter with which blockchain you are interacting, you need an account to interact with the blockchain. If there are no accounts, it is as good as no interaction with the blockchain network. Solana accounts are the fundamental data unit for storing all state on the Solana network. So what is the big idea? Solana stores all network state in one giant key value store. Every key is a 32-byte address and every value is an account. The different types of account in Solana includes wallet account, token mint account, and program account. Now each of these account has the same 5 fields. What are those 5 fields? First is Lamports. This field indicates the wallet's balance in Lamports, wherein one sol is equal to 1 million Lamports. Only owner can debit Lamports. However, anyone can credit Lamports into a wallet account. Secondly, we have data. So these are raw bytes or program code. Its size can be at max 10 megabytes, and only owner can write the data or update the data. Then we have the owner, which indicates the owner for the account. Fourthly, we have the executable field. If executable is set to true, it indicates it is a program that contains code. If executable is set to false, it indicates it is a data account or which stores the state of the program. At last, we have a rent epoch. This is currently replicated. However, if you want to make an account rent exempt, what you have to do is you have to set the rent epoch value to be the maximum value of unsigned day 64. Then we have two kinds of addresses. First is the public key. Now this has an associated private key. This is an ED25519 key pair. The public key is the address. The private key signs transactions, similar to what we have looked into Ethereum. Then we have program derived addresses. Now these program derived address, it does not have a private key. These addresses are derived deterministically from a program ID and a seed. The program which generates this address controls this address. What are the ownership and rent rules? Who can do what? First, owner program can modify data and deduct lamp ports. When we say deduct lamp ports, it is as good as I'm trying to send 10 sol to X. In that case, 10 sol will be deducted from my own account. Any program can add lamp ports to any account. Simply receiving sol tokens. Non-owners cannot touch the data fleet. Then owner reassigned only when data is zeroed. So this is a rent exempt balance. Imagine this to be a refundable deposit, not a fee. It scales with the account size. As the account size grows, the rent also grows. Rent is the number of sol tokens which you pay for your data to be available on chain at any given point of time. Let us look at some constraints. The account data is capped at 10 megabytes. The size of an address is 32 bytes. Max growth per instruction. Whenever a program calls any of the account, that is known as an instruction, and that instruction size cannot be more than 10 kilobytes. And at last we have a 64 bytes base override. So this is a quick overview of the Solana accounts in detail. What is the big idea? Then what different 5 fields each account has, what those fields mean, what are the kinds of addresses in Solana, then the account which owns the program, what it can do and what it cannot do. Then we have the rent exempt balance example. At last, the major constraints when it comes to account size of account data, the address size, and the max growth per instruction. Then after account, we have fees. So in Solana, there are two kinds of fees. First is the base fee, which is capped at 50,000 lamp ports. And second is the priority fee. Imagine priority fee to be a tip if you want your transaction to get included in a block as quickly as possible. Let us have a quick look into transaction fees in terms of Solana. What is a transaction fee? Every Solana transaction costs sol, which includes a base fee plus an optional prioritization fee. Base fee, it is always charged. So base fee is calculated the number of signatures into 5,000 lamp ports. Total fee consists of base fee plus the priority fee. Priority fee is nothing but the tip which you are willing to pay extra apart from the base fee in order for your transaction to be included as soon as possible into a block. So priority fee, this is optional. If you pass priority fee, there are higher chances your transaction will go as soon as possible. Coming to the fee distribution, where exactly the fee goes. The base fee is split into two halves, wherein the first 50% of the base fee is burned and the next 50% is given to the validator. However, the priority fee, it is given 100% to the validator. None of the priority fee is burned. So what are the limits and constants? In case of base fee, the limit is 5,000 lamp ports. CU here stands for compute units. So default compute unit per instruction is 200,000. The built-in instruction compute unit is 3,000. Fee is charged from the payer or the wallet which invokes the transaction, even if the transaction fails. So this is a quick overview about transaction fees in terms of Solana, which consists of base fee and priority fee. Base fee is always charged. Priority fee is optional. If you pass it, your transaction may get included into the block as soon as possible. Talking about transactions, so transactions are the way via which the clients interact with the network. In simple words, these are one or more instructions which are bundled and signed together by the accounts and sent to the blockchain network. Fourth, we have the programs. which are smart contract equivalent on the Solana blockchain. These are executable code which are stored inside an account marked executable. One thing to note here is, in case of Solana, the code and data are stored separately. The account which has code, for that account, the executable field is set to true. Whereas the account which has only the data part, for that the executable field is set to false. What exactly are programs in Solana blockchain? So programs are executable accounts holding on-chain code, which is stateless. It is compiled to SPBF, that is Solana bytecode format, and it can be upgraded. First thing is, the program is compiled to SPBF, which is Solana bytecode format. It is compiled via LLVM into Solana bytecode format, and it lives in executable accounts. Second thing, the program accounts are stateless. It does not have any state. All state lives in separate data accounts. Third, the program accounts can be upgradable. If you are using loader v3 programs, this can be upgraded by an authority. However, if you revoke that, it makes the program permanently immutable. Let us compare program versus data. Here we have a program account and here we have a data account. So in case of program account, the executable value is set to true and it is stored as SBTF bytecode. It does not have any mutable state. It is stateless. In case of data accounts, it is owned by a program. It holds mutable state, and this, you could say, state are passed via instructions. And we have seen for each instruction, the maximum size is 10 kilobytes. The instructions link the two together at call time. Here we have a quick look into the limits and constants when it comes to programs. If you want to go deeper, do check solana.com/docs/core/programs. After programs, we have programmed derived addresses or PDAs. So these are deterministic addresses which are derived from a program ID plus seeds. Now this seed value can be anything. You can pass any random value. However, when you combine or determine the address using PDA with a given seed and the program ID, the address will always be the same. Now these are the accounts a program can control without a private key. One question to ask here is, why these accounts do not have a private key? The answer is simple. The accounts generated by PDA do not fall on the ED25519 curve. Hence, they do not have a private key. And at last, we have cross-program invocation. Imagine this to be one contract or one program calling another program. So that is cross-program invocation, or in terms of solidity, it is contract A calling contract B. So to summarize, first we have accounts, then fees, transactions, programs, which is Solana's smart contract equivalent, then PDAs. One thing to remember here is PDAs the accounts generated by PDAs do not have a private key because they do not fall on the ED25519 curve. And at last we have cross-program invocation or CP. Let us now compare the accounts model of Solana versus Ethereum. This is the single biggest conceptual difference for developers who are coming from the Ethereum background. We are going to look at the different aspects and then we will compare how those aspects map with Solana and with Ethereum. So first, let us start with where does the state lives. In case of Solana, it has separate data accounts. That means the state variables which you write inside Solana programs are stored inside a different account and not in the smart contract itself. Now these data accounts program, these are distinct from the program's own account. Imagine this to be a proxy contract and the implementation contract, where the implementation contract has all the logic. Similarly, in terms of Solana, the logic contract has is the implementation contract, and the state where each of the state variable lives is the data accounts. Comparing that with Ethereum, it is inside the smart contract itself. The logic and all the state variables, everything is written inside a single smart contract. Second aspect is where logic lives. In case of Solana, that lives inside program accounts which are marked executable, and this hold only code. It does not have any state variable. So we have program accounts and data accounts. Whereas in case of Ethereum, inside the smart contract itself combined with data. Who executes these programs? On Solana, these are executed by validators via the Sealevel runtime. Imagine Sealevel to be a program which executes transactions parallelly whenever possible. In case of Ethereum, it is the EVM or Ethereum virtual machine, one node at a time per transaction. In Ethereum, there is no concept of parallelization, whereas in Solana, wherever possible, the transactions will be parallelly executed via the Sealevel runtime. At last, what triggers execution? On Solana, the execution can be triggered by incoming transactions, CPI calls from other programs. CPI is cross-program invocation, or you have scheduled execution. In case of Ethereum, incoming transactions or calls from other contracts. On Ethereum, the state and data lives inside the same smart contract. Whereas on Solana, you have separate data accounts and program accounts. What is the clock problem? And why every blockchain needs a way to agree on the order of events? First and foremost, distributed systems have no single trusted centralized clock. Yet, nodes must agree on the order in which transactions happen. Most blockchains solve this the hard way. How they do it? The nodes exchange messages and vote repeatedly until they agree that enough time has actually passed. Ethereum's approach that relies on external median timestamp, which is validated after the fact by the network. However, the cost of this coordination grows with network size. More the number of nodes means more messages means more latency. So Solana's reframing was, what if time could be encoded directly into the data itself so it never needs to be separately agreed upon? The developers at Solana found the answer to this question, which led to proof of history, and that then became proof of history with Tower BFT, Solana's consensus algorithm. So what is proof of history? It is a clock before consensus, Solana's core innovation. How exactly it works? We all know that each validator runs a sequential SHA-256 hashing function in which each output is given back as the next input. This is also known as verifiable delay function or VDF. The only way to produce the nth hash is to have actually computed the n minus 1 hashes before it. You cannot skip ahead. Data, like transactions, these can be mixed into these ongoing hash sequences, cryptographically proving that data existed at a specific point in the sequence. So what is the result? A verifiable, tamper-evident historical record of what happened where, without leaving a single node to talk to another. Apart from data, the timestamp itself is added cryptographically into the hash. So, the nodes or validators in Solana doesn't have to communicate explicitly with another nodes to confirm that what has happened and when it has happened. What EOH is not? First, it is not a consensus protocol. It does not decide which fork is canonical. It is not an anti-SIMI mechanism. That is, it cannot stop fake validators from joining the Solana network. It is purely a solution to the clock problem, which gives every validator a shared, verifiable sense of elapsed time. Consensus is Tower BFT, which is a separate layer that is built on top of proof of history, which we are going to cover next. So, Solana asked itself one question that led to the invention of proof of history, or POH. Proof of history is not a consensus protocol. However, when combined, it is combined with Tower BFT, which is Solana's consensus algorithm. Let us now look into the Solana Railroad. This is Solana's own explainer for why a shared clock speeds up verification. Other chain railways consider Ethereum blockchain. In case of other chains or Ethereum, there is no shared clock. What it implies? Imagine there is a train traveling through several stations towards Chicago. Then at every stop, the station attendant must contact every other station to confirm, did this train really depart me block? Is it really due here? In case of Ethereum, that is what exactly is happening. Each node is communicating with each other node in order to verify the data and the transaction. So this back and forth takes real time and resources at every single stop. The verification cost is paid again and again. How does Solana addresses this? Let us have a look at it. The Solana Railroad, which makes use of the shared clock. In case of Solana, every time the train stops, it receives a time-stamped stamp from that station. At each station, the train receives a stamp which has the timestamp. By the time it reaches Cleveland, it already carries stamps from Philadelphia and Pittsburgh, proof of its own history. So what does the Cleveland attendant do? It verifies the whole journey instantly from the stamps alone and their own stamp and their own stamp and send it on, so no phone calls are required. In case of Solana, there is no explicit peer-to-peer messaging in order to verify the data and the transactions, because the Solana blockchain carry forwards a shared clock which involves proof of history. By that, the validator knows that the data was actually present when it happened. Because of this, the verification needs only a small piece of information. It can also happen in parallel across many validators at once. Now the core crux, Tower BFT. It is the consensus which is built around the clock. This is the voting algorithm which is optimized to exploit proof of history. Traditional PBFT, or practical Byzantine fault tolerance, it requires multiple rounds of validator to validator messaging to agree on a block. In the previous slide, we have seen how that becomes expensive when the number of nodes go on increasing. Tower BFT, it keeps the core PBFT idea. However, it uses a shared proof of history clock to cut that messaging overhead dramatically. Because every validator can now independently read timeouts and state directly from the proof of history stamped ledger, a validator can decide how to vote using far fewer peer-to-peer messages. Each validator votes for the fork it considers heaviest. Whenever a new transaction comes in, so there are multiple forks, the validator decides which fork is the heaviest and casts its vote on that heaviest fork. The one with the most accumulated stake-weighted votes, and every vote commits that validator to a lockout period on that fork. Tower BFT, or stacked vote consensus. How validators commit to forks, escalate lockouts, and recover safely. In case of fork recovery, voters need a way back when their fork loses supermajority support. If you are a validator and you are voting on fork 1, what if that fork loses majority? You need a way to recover from that fork. Risk control. Each vote carries reward risk. Voters configure how much they accept. Then ASIC resistance. Consensus must resist attackers running faster proof of history hardware. How the vote tower works. Each new vote doubles the lockout of every vote beneath it in the stack. So, for the first vote, the lockout becomes 2 slots. Then when you do, or the validator does, a second vote, the lockout goes to 4 slots. Similarly, after 5th vote, the lockout becomes 32 slots. And at 2 raised to 32, the vote BQs and the rewards are paid to the validator. What exactly is a slot? It is the unit of time. Each slot has a designated leader that may produce a block. In case of Solana, it is 0.4 second. What is a vote? A signed validator lock hash pair signaling which fork a validator trusts. And what is lockout? It is a forced delay in slots before a validator can abandon a confirmed fork. What are the voting rules and how does Solana ensures ASIC resistance? A validator can only cast a new vote if all 3 conditions below hold. First is each validator must respect lockouts. Secondly, a threshold check. The block at stack depth 8, it needs greater than or equal to 2/3 of the network's peak voting for it or a descendant. Third, switching threshold. Switching fork requires greater than 38% of recent forks to already sit outside the current top fork. So these are the 3 rules each validator must follow in order to cast a new vote. Let us now look into ASIC rollback resistance. As we know, the lockouts double with every vote. The attacker hardware speed only grows linearly. So this is the first vote. The lockout is 2 slots. What is the ASIC speed needed? It must be 2x or twice. For 3 votes, the ASIC speed must be 2.6x or 2.6 times. In case of 10 votes, it must be faster than 102 times. Whereas in case of 20 votes, that becomes 52,428 times faster. So, at 20 confirmed votes, an attacker needs hardware over 52,000 times faster to roll back the fork, which discourages the attacker or the validator to act dishonestly and consistently vote on the fork which is honest and which is the longest or the canonical one. So this is how ASIC rollback resistance is implemented into the Solana blockchain and how Tower BFT along with VOH fits together and makes scalability as well as security the 2 prominent keys of Solana blockchain. In the top, we have said Tower BFT is optimized to exploit proof of history. How is that? To understand that, first we must understand the lockouts and the vote tower. What is a lockout and what is the vote tower? Every time a validator votes for a block, it accepts a lockout. What is a lockout? It is a forced delay which is measured in slots before it can vote for a conflicting fork. Imagine there are 2 ongoing forks. Validator 1 has voted for fork 1. So by default, validator 1 is now locked out for 2 slots. 1 slot is equal to 0.4 seconds on the Solana blockchain. Each additional consecutive vote on the same fork doubles the lockout of all earlier votes in the stack, which becomes the vote tower. So for the first vote, the lockout duration is 2 slots, which is 0.8 seconds. When the validator casts the second vote on that same fork, the lockout duration becomes 4 slots. After 3 votes, it becomes 8 slots, and after 20 votes, it becomes 1,048,576 slots. And now, if you want to roll back your previous votes, that would need an ASIC chip, which must be approximately 52,000 times faster. So this makes switching forks exponentially expensive the longer a validator has been voting on one chain, which is exactly what discourages dishonest rollback attempts. In case of Ethereum, you must log into each and every node and then recalculate the block hashes. In case of Solana, the same feature is being made in the form of Tower BFT, in which once you cast a vote on a particular fork, that applies a lockout period. And that lockout period keeps on doubling after each vote, which ensures that you stay honest to the fork in which you have earlier casted vote. And if at all you try to switch to another fork, if your lockout duration crosses 20 votes, that would require you an extremely super fast chip to do so, which discourages dishonest rollback attempts. How exactly the proof of history and Tower VFT fit together? These are two different layers, however, their goal is one. The goal is to achieve fast finality without sacrificing security. Proof of history ensures or minimizes the peer-to-peer messaging between the validators, and the Tower VFT discourages dishonest behavior. So proof of history, every validator maintains a continuous verifiable hash chain clock, establishing when things happened with zero messaging. Tower BFT validators vote on forks using that shared clock to minimize messaging, establishing which fork is canonical or which fork is the longest. Lockouts, votes accumulate exponentially, in turn growing lockouts, making honest consensus exponentially expensive to attack or reverse. Fast finality, the combination lets Solana target approximately 400 milliseconds of block times and rapid practical finality at scale without added round tricks. So this is how proof of history and Tower BFT fit together and adds to the scalability or high throughput of Solana blockchain. The remaining 6 innovations, what are those that the Solana ecosystem offers? First is Turbine. If you have used BitTorrent in the past, the format in which the data packets were transferred, that same format is being used by Solana, which ensures that the blocks are split into erasure-coded packets and fanned out across layers. Gulfstream, it is a mem pool-less transaction forwarding. Clients forward transactions to the next node leader ahead of time. Sealevel is a parallel smart contract runtime. It executes multiple transactions or independent transactions parallelly. Pipelining, it is a TPU or transaction processing unit that overlaps, fetch, signature verify, execute, and write stages like a CPU pipeline. Imagine pipelining to be a queue. Cloudbreak, horizontally scaled accounts database which are optimized for concurrent reads or writes across an array of SSDs. Archivers, similar to Ethereum, if you want to read a block, if you want to read data from a block number which is not the recent 10,000 blocks, in that case you have to query an archive node. So in terms of Solana, Archivers offloads long-term ledger storage to a separate class of lightweight non-consensus nodes. Then we look into the client-side development part. What are the different official SDKs Solana offers? If you are using Rust as the primary language, you can go with Solana_SDK. This is the official one, and it has extensive, a wide community and extensive support. If you want to go with TypeScript, go with @solana/kit, and they are also community maintained SDKs supporting Python, Java, Go, and so on. So what are the key takeaways? What you should be able to explain after today's session. First, the Solana development splits into two halves. First one is the on-chain program development, and second, the client-side development. Secondly, accounts are Solana's universal storage primitive. Programs and their data live in separate accounts, unlike Ethereum's combined contract model. POH, or a proof of history, is a verifiable sequential hash clock. It is not a consensus mechanism. It lets validators agree on event ordering without messaging. Tower BFT is Solana's PBFT style consensus, which is optimized to exploit that shared clock. Votes create exponentially growing lockouts that make dishonest folks exponentially expensive to pursue. Then at last, we have looked into 6 further innovations, which combines or which includes Turbine, Gulfstream, Sealevel, pipelining, Cloudbreak, and archivers. So these round out the performance stack at the propagation, execution, and storage layers. Let us do a quick knowledge check. On Solana, where does a program's executable code live relative to the data it operates on? Second question, what kind of function does proof of history use as its core cryptographic clock mechanism? Question third, which statement correctly distinguishes proof of history from Tower BFT? Fourth one, in Tower BFT, what happens to a validator's lockout period with each additional consecutive vote on the same fork? And the fifth one, which Solana innovation is responsible for parallel execution of smart contracts across GPUs or SSDs? At last, what is Gulfstream primarily designed to eliminate?